It's an exciting day, everyone. Hello, Dr. Jenkins here, because this is going to be our first chapter on an actual nutrient. What better place to start, especially for an athlete, than carbohydrates? I'm excited, folks. Here we go. Here's an outline of what we're going to be talking about. I'm thinking about splitting this lecture into two parts. So the first part, we'll get through as much as we can, and then we'll finish up in video number 2. Now, the beautiful thing is that we introduced the basics of the macronutrients already in chapter 2 when we talked about the basic structure and the basic function. So the beginning of this is really just a review. Let's go with red. So remember, in terms of structure, we have simple carbohydrates, which would be the monosaccharides, which is a 1 sugar, and the disaccharides, which is a 2 sugar. And then we have complex carbohydrates, which would be many sugars joined together, or polysaccharides, because poly means many. Be able to give an example of each. And I have, because I care about you so much, to try and make sure that we're clear, I've put stars beside the ones I would like you to know. So you should obviously know glucose. That's the form of simple sugar that circulates in the bloodstream. I'd also like to add fructose. It's another type of monosaccharide where it's just a 1 sugar molecule. But I'm including it because we're going to see it in some sports nutrition products. Make sure you can give an example of a disaccharide, and the one I gave before, and I'll give again, is sucrose. Sucrose is table sugar. So if you put sugar into your coffee, that's an example of sucrose. It is a disaccharide. And then be able to give 2 examples of polysaccharides, starch and glycogen. And just to review, but you already remember, we remember what glycogen is. Glycogen is stored sugar or stored glucose. So a lot of times we have so much glucose and we don't need it all at once to stay in the bloodstream, so we can store it. And the storage form of glucose is called glycogen. Now, just like before, you don't have to worry about the specific structure, but I just like to include pictures just to give you an idea of what it looks like in terms of its chemical structure. And because we're going to be getting more in depth in this chapter, let's talk about some specific examples. I already told you about sucrose, so that should be a review. Sucrose is a disaccharide, 2 sugars, and an example of that would be table sugar, which we can see a picture right here, obviously. Glucose, which we talked about, glucose is what circulates in the blood. So you should know that. Glucose is the monosaccharide that circulates in the blood and then goes into our muscle cells, which of course gets converted into ATP, because we remember ATP is a usable energy source. But there's a reason that I wanted you to know fructose. Fructose would be something, it's a form of a monosaccharide that we see in some sports nutrition products. So one example here that you may be familiar with is a goo packet. It basically kind of tastes like icing, not quite as sweet, but it's a gel form, so it's quick to digest. It contains fructose, which means that it's already in a simple form and easy to digest, absorb, and metabolize. So some things to point out: fructose is quick to break down because it's a monosaccharide. It's already in a simple form. And we can actually ingest this right before and during activity. A goo packet is something that a marathon runner would probably benefit from, because it gives us a good form of monosaccharide that's easily absorbed and can be converted into quick energy. Some people will take it in right before activity, but also certainly it's an acceptable during activity food gel. And then starch, which is an example of a polysaccharide. This is going to take longer to break down than the fructose, but once we do break it down, it gives us more energy, a little bit more robust, because of course it's more complex, it's got more sugars. This would be best to ingest several hours before or after. So this is something you don't want to ingest during activity because it's simply too complex. So it's going to require more energy to break down, which could potentially take energy away from our muscles. But certainly the night before, a couple hours before, a couple hours after, it's a good way to replenish our sugar stores. Quick story here, as you probably have already seen from Blackboard, and I think I mentioned it before. I did the Ironman a couple times, Ironman triathlon, and I remember, I'll never forget, on the bike, there was one dude who had made a baked potato, I guess, that morning, and had it in foil, and then during the bike, I was right beside him, he pulled this baked potato in foil out of his back jersey pocket, opened the top, and just squeezed, and just ate the potato out of the middle. That wouldn't be my choice, but in terms of the Ironman being so long, I suppose it wouldn't be the worst choice. Okay, we already know the functions of carbohydrates, ladies and gentlemen. We know it is an energy source, what our cells go to first, right? We know that our muscles are going to, for the most part, burn a carbohydrate and fat mixture. But our first energy source, because it's so quick to be broken down, is carbohydrates. We will utilize blood glucose first, and then we can also break down that stored sugar. We can break down glycogen, but we'll first use the blood glucose immediately in and around the muscle. Something I didn't talk about before, but I do want to point out now, is that carbohydrates are the only form of energy that our central nervous system can use. That's pretty interesting, I think. So we're talking about our brain. If I could draw a brain, that's a really bad brain. Our brain and spinal cord, that's what's considered our central nervous system. Of course, these consist of a gazillion cells. Well, the only fuel that they can use is carbohydrates. So the central nervous system cells cannot burn fat or protein for energy. This isn't a problem if you get enough carbohydrates, and most of us do. But if you think about some of the extreme Atkins diet, I know the ketogenic diet is really popular now, and I'll talk about this more later, but for most people, for most athletes, the ketogenic diet is not a good thing. But if we talk about a diet that really limits carbohydrates, if you limit your carbohydrate intake too much, you might be limiting fuel to your brain. And ladies and gentlemen, that is not a good thing. Okay, you can read here what's at the bottom. You don't have to know this right now. If you have enough carbohydrates, that means that you're not going to have to use too much protein for energy, which is a good thing. And if you have enough carbohydrates, it's going to prevent you from burning too much fat, which can put you into a state of ketogenesis, which can actually be very detrimental. Don't worry about these now because we're going to talk about it later. But these first two functions, yes, yes, yes. All right, just took a little drink there, I'm sorry. What about the dietary intake? Well, we've already talked about what percentage of the diet should come from carbohydrates. So for most people, whether you're sedentary or whether you're an athlete, for most people, somewhere between 45 to 65% of our diet should come from carbohydrates. And we get that range to satisfy whatever our needs are. You can see that the dietary reference intakes is about 130 grams daily. But I don't like to use that because that really depends on your age, your height, and your weight and your activity level. So I don't think that really gives us a good ballpark necessarily because we're all so different. You can see how the recommendations break down according to the old My Pyramid. Of course, now we're on My Plate. The old My Pyramid would give you some servings ideas. You don't have to know these. I included some averages down below in terms of grams. You don't have to know these, but I'm just throwing out some numbers so you get more familiar with them. So you can see we're talking about 200, 300, 400 grams of carbohydrates per day. Just gives you a ballpark, so you know that if someone has 50 grams of carbohydrates per day, that is very, very, very low, not enough. Or if someone said to you 1,000 grams, that is also not right. But for now, just know the AMDR, the percentage. Okay, we're also going to review some of the information that we introduced about carbohydrate storage and carbohydrate metabolism. We talked about these in chapters 3 and 4, I believe. Okay, so we may recall that carbohydrates is what our muscles are going to go to first for energy. But within that, they're first going to go to glucose, the blood glucose. And I've already talked about that. I'm just putting it on a slide to make sure we understand. So there's glucose in the bloodstream, and that is what our muscles will suck up first. And then we'll be able to break down some glycogen back into glucose. And then to use that glucose. I want to point out where we store glycogen. 2/3, and I think this is on a slide again, but hey, the more times we can go through it, the better. Oh, I think I have that backwards too. Yeah, 2/3 in the skeletal muscle. All right. What we're going to see is that 2/3 of all of our glycogen stores are in the skeletal muscle. And that's by design. Our muscles need a lot of energy. So it makes sense to have a large glycogen store right there. And the remaining about 1/3 of all of our glycogen is stored in the liver. And then, of course, a little bit later in duration, we'll turn to fat. And I still want to point out that we tend to burn a carb-fat mixture. So even though we go to carbs first, your body is going to want to go to fat as quickly as possible. And for most of our activities, we're burning a carb-fat mixture. But it is carbohydrates that our cells can metabolize first. Now, I'm going to change color because I included our energy systems here because everything goes together. We can't forget what we already learned. So remember we said that there's systems, and the first energy system, which is really just a way of saying a series of chemical reactions that will produce ATP. But maybe, I remember we said like the first 10 seconds of activity, we can utilize an energy system called the intramuscular high energy phosphate. Yeah, we said that. And in that system, we'd be using glucose right from the bloodstream. When we get to the next one, which is anaerobic metabolism, which can give us an additional maybe 90 seconds of energy, and then anything after that would be aerobic metabolism. Well, once we start to get into the anaerobic metabolism and even the aerobic, we're going to start to use glycogen. Just putting it all together for you. You're welcome. All right. Where do we store? Well, the glucose is in the bloodstream, and then our glycogen. We store most of the glycogen, about 2/3, in the skeletal muscle, and the remaining 1/3 in the liver. You don't need to know these numbers, okay? But what I want to point out is we can store a lot of glycogen. That's phenomenal. We like that. We can store a lot of glycogen. In fact, depending on the source that you read, if we were to just take you right now, whatever you're doing, you're sitting there, you're out in the sun, you're whatever, if we were to take stock of your glycogen storage right now, the glycogen in your skeletal muscles and the glycogen in your liver, using that energy, you could potentially run 20 miles. Now, maybe you're not quite trained to run 20 miles. I don't know, maybe you are. But my point is, it's so much energy that we store as glycogen that it would be enough energy to fuel a really, really, really long run. Now, would you be able to do that 20-mile run? Probably not for a lot of you, but it wouldn't be because of lack of fuel. It would be because your muscles aren't trained, or because your energy systems aren't adapted to be able to use the fuel as well. But the point is, that fuel is still there. Those fuel storage tanks are there. Okay, something that we haven't talked about yet is regulation of blood glucose. And I want to add blood glucose because we're talking about regulation of blood glucose. We want to make sure in our body that we have an appropriate amount of blood glucose circulating in the bloodstream at all times. For most people, it's somewhere between, 60 and 80 milligrams. Some will even say you can have up to 100 milligrams. So if you wanted to be a little bit more broad, we could say somewhere between 60 and 100 milligrams. You don't have to know that number, but I just wanted to give you a number in case you were wondering. But we want to make sure that our blood is sufficiently stocked with blood glucose. We don't want too much, because that can create a lot of problems. So we also don't want too little, because then we're going to be starving our cells of energy. So the process of maintaining the appropriate amount and then maintaining the appropriate amount as conditions change. Let's say your body is maintaining 80 milligrams of blood sugar, but then you go and you run. You start running 5 miles. Well, your blood sugar is going to take a quick dip. So our body has to be able to react to that to keep our blood sugar from dipping too low. On the other hand, what if you just ate a big meal? Well, then your blood sugar is going to spike. So we have to have a means to not let your blood sugar spike too much. And the way that we maintain this balance of keeping just the right amount of blood sugar in our bloodstream is through hormones. And we talked about these hormones because they're produced by the pancreas, which happens to be a digestive organ because it produces digestive enzymes. But the pancreas also is an endocrine gland, which means that it produces hormones. And what are the hormones? Make sure you know these: insulin and glucagon. I can see that my characters didn't show up here, but that's why I got this fancy pen. Insulin is released when blood sugar is high. Glucagon is released when blood sugar is low. You need to know these. So if you have a big meal, your pancreas will release insulin. And even though these hormones are released from the pancreas, they have their action at the liver. You should know this also. The hormones are produced and released by the pancreas, but then they travel to the liver, because the liver is where we can store glucose as glycogen, or we can break glycogen back down into glucose. It's a great system when it works as it should. So if we have a big meal, then we're going to release insulin because our blood sugar is going to go up all of a sudden. And what happens is insulin tells the liver to store glucose as glycogen. So if you think about it, like our initial problem is that we have too much blood sugar all of a sudden. To help fix it, the liver takes the glucose out of the bloodstream to store as glycogen. But because the liver takes glucose out of the bloodstream, the remaining blood sugar goes back down to normal. And then the opposite is true of glucagon. It's released when blood glucose all of a sudden drops. Glucagon is released from the pancreas, but again goes to the liver, and it tells the liver to break down the glycogen stores into glucose, which means that our initial problem was that our blood sugar is too low, but then glucagon, we release glucose back into the bloodstream to bring it back up to normal. You may not like charts and graphs, but this is a science course. We can't get away from it. And they are very, very illustrative. So, check it out. Here's our glucose norm. Think of it as a balance beam. We want this to be somewhere between 60 and 100 milligrams. I'm not going to ask you that number, but I'm just putting it on here just because. What if you ate a bunch of Pixie Sticks, even if you know what those are? I don't know. What if you had 10 Red Bulls? There's a lot of sugar in that. Then your blood sugar is going to go up. Remember, what hormone is released when blood sugar goes up? Insulin. If our initial problem is too much blood sugar, we release insulin, which goes to the liver, and tells the liver to pick up that glucose from the blood and store it as glycogen, thereby lowering blood glucose back to normal. This is called a negative feedback loop. If we have a problem, we do the opposite, or we reverse it to bring something back to normal. On the other hand, if you haven't eaten for a while, like this dude, if you haven't eaten for a while, he's dreaming about food, your blood glucose is going to go down. When blood glucose goes down, we release glucagon, which goes to the liver and tells the liver to break down glycogen back into glucose, which is released into the bloodstream, thereby increasing blood sugar back up to normal. This is good stuff, folks. We could also think about this in terms of exercise. If you are resting, like Homer is here on the couch, you're likely to be eating and resting. Your blood sugar goes up, so you're more likely to release insulin or bring it back down. But if you're exercising, you're more likely to have a drop in blood glucose and the need to release glucagon. Good stuff. All right, I'm going to end there, and we'll finish the rest of this in video 2.